Assalamualaikum warahmatullahi wabarakatuh and good evening to my beloved lecturer. My name is Mama Hamdani bin Mama Khalil. Today we want to explain about the fractography study of weld joint of carbon fiber polyphenylene sulfide. Scientific objective. The objective of this research is to do fractographic investigation of the fracture surface in thermoplastic composite made of polyphenylene sulfide, reinforced with continuous carbon fiber that are weld together. Next, another purpose of the study is to examine and comprehend these fracture surface properties following lab shear loading. The main objective of the research is to give a thorough understanding of the fracture surface in thermoplastic composite weld joint, with an emphasis on evaluating addition at different interfaces and figuring out the variable affecting these joints' mechanical characteristics. The specific objective of the experiment is to perform a detailed fractographic analysis of the fracture surface to evaluate the quality of interfacial adhesion between the carbon fiber and the polyphenylene sulfide within the composite, to assess the interaction between the polyphenylene sulfide matrix and the heating element in the weld joint. Next, to identify and understand the failure mechanism that involve. Examine how the processing conditions during welding affect the consolidation of the composite. To characterizing the lab shear strength values of the weld joint.
Today I'm dealing with the introduction part and I'm going to talk about the fractographic analysis of welded joints of CF PPS composite, which is a structural composite. The PPS is polyphenylene sulfide and CF is carbon fiber, which is the reinforcement. The structural composite is a multi-layer and normally low-density composite, which is used in applications requiring structural integrity, high tensile strength, and compressive strength and stiffness. So these structural composites are mainly used in aerospace industry, and resistance welding is used for joining structural parts. Resistant welding efficiently joins structural parts with thermoplastic composites. This process melts semi-crystalline polymers or softens amorphous ones while preserving their properties. It involves applying pressure to consolidate the joints and promote interdiffusions of polymer chains. Now let's look at the factors affecting the performance of the structure, which is the reinforcement, the carbon fiber, and welding parameters like temperature, pressure, time, electric current, etc. affects the performance of the structure. The efficiency of the welding process can be assessed from the failure mechanisms present in the welded regions. Three types of failure modes are usually observed in welded joints. Interfacial interface between the heating elements and the laminate is not adequately consolidated with the detachment of insert. Interlaminar, a failure of matrix adjacent to the bond line. The specimen failure, which is the laminate rupture far from the welded surface. In this context, the study of fracture surface by fractographic analysis has become a key importance in qualitative evaluation of causes of failure in welded joints. Fractographic analysis helps identify and understand the morphological aspects, correlations with material processing property, and interpretation of the fracture surface.
I am continue to explain the methodology of this experiment. Firstly, material selection. 2.5 mm thick solid laminate of 5HS carbon fiber close reinforced polyphenylene sulfide composite were used. Secondly, specimen preparation. In accordance with ASTM D5868 guideline, cut the carbon fiber and polyphenylene sulfide laminate to the dimension appropriate for lab shear testing. For every wet family, 5 specimens measuring 100 mm by 225 mm were prepared. Thirdly is resistor welding machine. Created and construct a resistor welding device on demand. Between the laminate are integrated connectors to a heating element or electrical resistive element. Require 5 to 70 ampere of electrical current, zero point 0.2 to 3 megapascal of pressure, and 1 to 300 seconds of time. 4. Design of experiments for welding parameters optimization. Use three factors in a thorough design of experiment: pressure, current, and time. This is for the to determine appropriate welding parameters. 5 replicates will conduct in the center spot. Next, the welding process. Place a stainless steel mesh insert that conducts electricity between two laminates. Apply pressure that aids in the polymeric chains interdiffusion mechanism during the welding process. Various welding parameters that fall within the range established by earlier experimental testing, such as time, current, and pressure. Next, lab shear test. Perform a lab shear test in compliance with ASTM D5868 guideline. Use a room temperature Shimizu test machine that was universal and had a crosshead rate of 1.5 mm per minute. Furthermore, fracture surface generation. Produce fracture surface under the identical circumstance as the mechanical test after lab shear test. Fracture surface shield by a thin layer of plastic. Using a diamond disc, cut the weld area in order to analyze it. Next, use a SEM analysis. Using a dry airflow, fracture surface were cleaned to get rid of the cutting debris. Sputter coat surface to achieve a gold film of 4 conductivity. Use an FEI Inspect S50 microscope to analyze fracture surface via scanning electron microscopy. In addition, analysis of fracture surface. Numerous fractographic features such as river lines, curves, and fibers with a thin polymeric matrix layer covering them. Evaluate the fiber or matrix and matrix or heating element interfacial addition. Unexpected features were examined, namely global patches that show effort in mode during testing of lab shear strength. Next, statistical analysis. ANOVA was used to examine how the independent factors pressure, time, and current affect the lab shear strength. Regression equation was created to comprehend how welding parameters affect lab shear strength. Furthermore, identification of optimal welding parameters. Based on the result of lab shear strength, the optimal combination of welding conditions was determined. Analyze how strength values are affected by mechanical inquiry and the interdiffusion mechanism. Lastly, documentation and reporting. Record the specific outcome and observation of the experiment. Produce a thorough report that summarizes the fractographic analysis of the fracture surface in thermoplastic composite weld joint.
Hello, my name is Muhammad Fidaus bin Isir. My ID number is SC21034. I will present the result and discussion of this journal. Spectrographic evaluation of features surface. Figure 2 shows typical image of the weld area of the carbon fiber over polyphenylene sulfide laminate following the lab shear test. In this mechanical test, the specimen with the greatest lab shear values with tearing the metallic insert indicating that the heating element was in close contact with the polymeric matrix. The specimen exhibiting the lowest lab shear value indicate that during the test, the insert separated from one of the laminate surface. SEM of joint with higher values of flat shear strength. Figure 3 shows image of fracture stress of the weld joint with higher lat shear strength value 70.1 plus minus 1.4 megapascal. This figure demonstrates the good consolidation that the carbon fiber over polyphenylene sulfide laminate provide. It clearly shows that the CPS metric group include the carbon fiber even after the loading. The picture shows that the reinforcement has been well implemented by the polymerimetry and that there is a strong interfacial contact between the fiber and metric. Figure 3a shows shear cups that have formed in the voids between fibers. The metric abrasion region is used to define the fragile fracture characteristic it shows in figure 3b. This feature is linked to the relative movement of surface as well as height loading rates, which in the case of semi-crystalline thermoplastic may result in metric cleavage or transcrystalline area fracture. The fractographic examination also reveals features like the river line traces and the broken fibers, which are all seen in polymeric areas in figure 3c. Intralaminar failure is indicated by these features. These features is consistent in shear failures and offer limited insight into the cause and direction of the breakdown. Plastic deformation and the presence of fiber imprinting in figure 3D is shown. These latter features result from the viscoelastic properties of the thermoplastic matrix. The heating element with the filament recovered by a thin layer of polymer matrix seen in figures 3E and 3F. This feature implies that the impregnation procedures happen effectively over the heating element. SEM of joints with lower values of lat shear strength. Figure 4 shows image of the fracture surface of the weld joint with lower lat shear strength values, which is 1.3 plus minus 1.1 megapascal. The processing conditions that were not favorable to the welding of laminate had an impact on these outcomes. The insufficient PPS interdiffusion mechanism between the carbon fiber and polyphenylene sulfide laminate and the heating element mesh characterize this laminate group. This due to lack of enough heat and pressure in this area without influence of the stainless steel heating element mesh. Study on the interfacial adhesion CF over PPF and heating element over PPF. The interfacial adhesion of the polymeric matrix and the heating element is significant factor in the fracture strength of welded laminate. As seen in figure 2 from previous slide, there is a chance of polymeric matrix overheating element debonding when a weld composite is mechanically stressed and exhibits a weak interface area. Figure 5 shows the cohesive fracture of the polymeric matrix and the presence of fracture fibers, which are caught in a thin layer of polymeric matrix. Demonstrate a good fiber polymeric interfacial adhesion. This characteristic draw attention to the strong interfacial adhesion that exists. Figure 6 shows when the welding processing settings are appropriate to enable PPS melting and a chain interdiffusion mechanism between the metallic mesh filament, the interaction of polymetric with the heating source. Figure 6a shows that a strong anchoring of PPS metallic on the metallic filament is provided by interfacial addition of polymeric matrix and the heating element. However, as shown in figure 6b, the polymer matrix exhibits a poor interaction with the metallic mesh in several specimens with lower shear strength values. This is likely due to processing parameters that were used which does not favor the polymetric impregnation between the metallic mesh filament. Figure 7 shows the existence of void in the PPS laminate structure surface close to the weld interfacial area. In figure 7a, the additional aspect that could have contributed to the poor adhesion between the polymer matrix and the heating element and the fiber is exist of void in the polymer matrix Vacuum can arise the thermoplastic composite from a variety source, including moisture, leftover solvent, air trap during molding, inadequate compaction, pressure during molding, nucleation under low stress condition, and plastic deformation of the polymetric. As seen in Figure 7b, in this instance they are able to grow during the plastic deformation, most likely as a result of viscoelastic nature of polymery. The composite flexure surface is straight when the void merge. Intralaminar and interfacial laminate failure may arise from the existence of void in the matrix, more specifically in the interfacial area where damage propagation along the fiber matrix contact can initiate the failure process. Figure 8 shows the continuation of mechanical stress might cause the polymer matrix to rupture and generate polymer droplet features on the fiber surface. In this instance, the polymer deforms plastically in the polymeric matrix up until a point at which it degrades and shrinks into a spherical shape like a droplet of a fiber.
In conclusion, the result shows how important fractographic analysis are in characterizing materials. These analyses complement mechanical characterization and aid the processing optimization of the materials. The plastic deformation in matrix-rich region are identified, attributed to PPS viscoelastic behavior. Specimen with higher shear strength display shear cusp aspects in cohesive matrix fracture and fiber matrix interface. River marks aid in identifying failure propagation direction, indicating good fiber matrix interface. Specimens with lower shear strength exhibit poor adhesion at heating element matrix interface. Mechanical anchoring is the main adhesion mechanism in these cases. The presence of voids in the matrix and fiber/matrix interface may be linked to moisture or residual solvents, leading to interfacial failure. Voids nucleate due to polymer matrix plastic deformation, contributing to interfacial failure.